Hello, I'm Professor Ito. On this topic, I'd like to speak for the next 40 minutes. Now, first, about the outline of my talk today. I will discuss the projects I've been involved in, which Professor Okoshi just mentioned. What does a circular economy mean? I've been involved in polymer research on plastics. And the circular economy for plastics has been a hot topic in Europe. If you look on the internet, you'll find lots of discussion about this. Plastics are all around you. Actually, plastics were developed about 100 years ago. Around us, there are ceramics and metals. They were replaced with plastics, and now they're everywhere. There has been mass production, mass consumption, and mass disposal. The model for plastics has been to manufacture them, then either throw away, incinerate, or use them in landfills. But we'd like to find ways to use them longer, so that resources can be circulated instead of wasted. That is called a circular economy. I've been involved in projects related to such a circular economy. You may have heard of the term 3R: reuse, reduce, and recycle. The 3 R's. When you hear circular economy, people often think of recycling, but reuse is the most important. We want to use products over a longer period, but plastics are brittle and often get discarded. But if you have tough, durable plastics, like watering cans, which are usually made of metals, but if they're made of plastic, that's better. We'd prefer brittle plastics to have a longer lifespan. That's crucial and has been explored in the IMPACT project. IMPACT is for motor vehicles, making plastics into tough polymers. Another thing, products used for a long time can be disintegrated, separated, degraded, and reused. If that's not possible, what do? Molecules can be broken down and recycled through chemical recycling. That is crucial. I believe the previous speaker was Professor Nozaki. I'm certain she touched upon this. This process is termed chemical recycling, and globally it has become a major research focus. There is a lot of research happening around it. Worldwide, some materials can be collected and recycled, but not all plastics are collected. For example, if you go to the ocean, you'll find PET bottles and other plastics thrown away, and consider the wear and tear of tires. As they break down into powders, many end up in the water. These tires, vehicle tires in particular, degrade into particles that flow into our waters. Since they don't degrade easily, they accumulate and pollute the ocean. And collection becomes challenging. For those that can't be collected, ideally they'd be naturally degradable, returning to water and CO2, which plants could then absorb, and potentially be a source for new plastics. Instead of using oil-based polymers, we might develop biomass-based ones, an essential part of the circular economy vision. For some, plastics might be an unfamiliar concept, but many materials in our world are essentially plastic, rubber, fiber, or even gel-based. Others include glass and ceramics. As mentioned earlier, this category encompasses rubbers like tires, textiles, fibers, clothing, and various gels. Indeed, these are all polymers. Interestingly, our body's DNA and proteins are also polymers. In essence, polymers differ from metals and ceramics in that they are lightweight, primarily composed of carbon, hydrogen, and oxygen atoms, all of which are lightweight elements. Whereas metals are the primary material for airplanes, alloys are also commonly used. But indeed, there are composites. Epoxy resin is used to surround carbon fibers as reinforcement. And all of these are composites. The general mindset used to be that aluminum was used, but now they're polymerized. Now in the future, not just in airplanes, but in automobiles, such polymers will be used. Because if you use polymers, the weight will be halved and the mileage will be doubled. Therefore, polymers will be used more and more going forward. And as I said, we need to think about what we're going to do with the polymers that are abundant around us. Okay, here I'd like to first talk about slide ring materials. Because polymers are brittle, as I said. But why? This is an illustration or diagram of a polymer. It's like spaghetti. It's like a string, a molecule, and they're bound with this cross-link. A tire is one example. These polymers are cross-linked and made into tires. When you connect them, they become very strong. But when you pull them, they will break apart. The lengths are really different, so the shorter segments are under lots of stress. That is why it is considered to be brittle. And to solve this issue, Japanese researchers came up with very innovative ideas. For example, Dr. Gong from Hokkaido University came up with this idea called double network, where the hard and soft networks will be put in order. So it's going to be very strong and will not break even if run over by cars. And Dr. Haraguchi included clay to come up with a very strong point molecule. And then Dr. Saki came up with the tetra peg gel. These same length polymers, called star polymers, will be connected. And when you do that, the stress will not be concentrated. It will be dispersed, which will create a very strong gel. And we used a different approach to create a strong, durable gel, which are called topological supermolecules. So, this is a molecule, kind of like a wisdom circle. It's called catenon. These rings are held together like this, and they're not chemically bound, but they will not come apart. These are called topological supermolecules. Other examples include rotaxane, where there's an axis in the center of the ring, with a large molecule on both ends, so that they won't be pulled apart or separated. Polyrotaxane is like a necklace with many rings. And this polyrotaxane was introduced in 1992 by Dr. Harada. In our research, we decided to cross-link these rings of polyrotaxane. What's unique about this is that, unlike typical cross-linking, we don't directly connect the strings. Instead, we first use these rings to thread through and then connect those rings together. We cross-linked them, as we did in 2002. Actually, this was first discovered by Professor Okumura when he was a student. Now he's a professor at Kyushu University. So, when you pull them, these cross-links or the rings will move. You may recall the concept of a pulley from elementary school. The pulley will move, ensuring that the string receives even stress. This means the tension will be equalized, and we believe a similar phenomenon occurs at the molecular level. At first, the length varies. But when pulled, the rings move, spreading the stress to ensure equal tension across the string. This is known as the pulley effect. It's already being utilized in anti-scratch coatings and also on the surfaces of golf balls. This technology is actually used by Hideki Matsuyama, the professional golf player. The balls are actually being coated and it gives a spin. I actually tried this myself, but when I do, it doesn't really work. Now, getting back to the topic of science. Recently, we have seen major progress. What was it? Traditionally, when you develop such a necklace, these are the number of rings that could be contained. If it fills to 100%, then the number of rings in this case would be 25%, so there is some space in between. But in our laboratory, a postdoc, Miss John, studied this, and this 2% coverage necklace was made. That was a successful development, and with this spacious necklace, if you cross-link with the ring, it becomes very tough, very strong. When there are too many within this distance, it cannot be elongated. But if you make a 2% hydrogel, you cannot pierce through. And it contains 80% water. But you cannot cut it with cutters. It becomes very strong. Back when it was made, we didn't know why it was so tough. But then the reasons were found out about 3 years later. And here is the scheme, as I said earlier. This is made of pulleys, the material's made of pulleys. And when you pull, what happens? Part of the ring moves. The ring moves. And when the ring moves, then the chain becomes exposed. And they align with each other. Then what happens is that they crystallize, and hard crystals are formed as a result. The gels will not break. And if you release the strength, the crystals break and it goes back. This is called elongated crystallization. It happens with gel. It was a discovery made for the first time with this. As a result of this crystallization, the gel was made extremely sturdy. Thanks to this development, various gels have been made. High-strength gels have been created. And vertically, you're looking at the work of rupture, the strength of the gel. And horizontally, you're looking at the recoverability. As it's evident, as you can see, as in the case of double network hydrogels, the strength of the gel was strong, but the recovery was poor. But in the case of this gel, the part of the crystal breaks very easily, making it harder. But if you release the force, it recovers very quickly. And that was verified with radiography. But I won't delve into any details. Such tough materials have been developed with new concepts. And that's the type of research I've been involved in. And then, starting in 2014, I became involved in the IMPACT project, which was a major national project. In 2014, the project, IMPACT, began. Various program managers were involved. In this initiative, each had a different area of research. I was involved in tough polymer, full-body polymer vehicles. Some were involved in robot development, or using spider thread for sturdy materials. There were various other projects initiated, and in our project, cutting-edge science or chemistry, as well as synchrotron radiation and supercomputers were used so that toughness could be improved, even when a crack was present and not propagating. Even with a crack, if you apply force, it doesn't widen or propagate. It won't break. With flexibility and safe recovery, it can disperse the force and initiate self-healing, which is very important. Even if it breaks, it can heal itself, and then deterioration and degradation can be halted. Destruction can be prevented, meaning the material can be used for a longer period. A longer lifespan can be achieved through this process. To do so, in Japan, including Tokyo, top-tier researchers collaborated on this. From the field of physics, we saw researchers of various disciplines join. But the project was spearheaded not by academia, but by private companies. These are the companies that participated, and they wanted to develop tough polymers, joining forces with both companies and academia. They worked together to develop new materials. That's really been the objective of the project. That was the project where we developed the polymer for automobiles. We worked on this for about 4 years. I don't have enough time to explain everything we achieved, so let me just go through 2 examples. One is the collaboration with Toray. We worked on polymer nylon used for stockings and more. You might have heard of this. It's also used for automobiles. It's a very strong and tough polymer. It's excellent, but it's not very elastic. When pulled, it might stretch about 10%, but then it will break. We wanted to enhance its toughness, so we added rubber to improve its elongation. However, this made it very soft and flexible. Balancing strength and this tensile elongation and maintaining hardness is a trade-off. If you prioritize one, the other suffers. But in collaboration with Toray, we modified the nylon into a necklace-like structure. Because of this, we were able to increase the elongation tenfold while maintaining the same strength, and it didn't break. What's impressive about this nylon sheet is when we conducted a bending test to see its limits. Ordinary ones would break after 2,000 bends, but with just 5% of the necklace structure added, it withstood 90,000 bends without breaking, indicating a 50-fold improvement in durability. This means it can be used for a much longer time. It's a highly durable polymer, which is crucial for advancing towards a circular economy. In the iron drop test, typical polymers or plastics would shatter upon impact. This is a hazard in vehicles as debris can scatter. But with our tough polymer, featuring the necklace structure in nylon, it doesn't shatter. It compresses, absorbing the impact energy. There are no small fragments produced. The way it reacts to force is entirely different from conventional polymers. This is a composite material designed for airplanes. We can expect the same level of impact, and the durability has improved threefold. So this is one of the achievements that we made. The next example is the one we worked on with Bridgestone, which is a tire manufacturer. They wanted to create tough tires or tough rubber and aimed to reduce the pressure of the film of the tire by half. The rupture energy has increased by about 4 times. And they applied this to the caterpillar. There's a rubber caterpillar. They tested it on a rough road, and wear was reduced by 60%. This means that if you use this rubber formulation, the wear is significantly reduced. It's very tough. It does not wear out so quickly. You can reduce the pressure by half, and the wear is halved compared to usual. developing strong polymers. Both strong and tough is crucial for the environment. Here, these are rubbers on the top and bottom, and we're trying to pull them. We inserted scissors. And the top one is regular rubber. After you pull them, you insert the scissors, and the rubber at the top ruptures. But the bottom one does not, due to its lack of crack elongation, indicating high durability. Usually, when polymers break, a void appears, which becomes a crack, and the crack elongates, leading to rupture. But in this case, it does not happen, so it does not break easily and can be used over a long period of time. This is the double network I talked about. This principle was applied. These were some of the achievements we made, and we are trying to implement them, having also published our findings in various scientific papers. We've collaborated with several companies on these outcomes, and we wanted to make those outcomes visible to all of you. Actually, all those companies have developed parts for automobiles. Once they are made, and if combined, we thought we might be able to build a vehicle. So here is a concept of a vehicle that was developed. And you are looking at the image of this concept car. And it actually runs, even though it's a concept car. The speed is up to 150 kilometers per hour. And the weight is half that of conventional vehicles. But 90% of it is made of plastics. The motors and batteries could not be made with plastics. But most of the parts are plastics. Even the springs in this vehicle were made of plastic. We built it, and it proved to be very strong. Then we tested it on a circuit, trying to demonstrate that it doesn't break. Here's the photo, or the video, from the presentation at the Prime Minister's office, where the former Prime Minister participated in our experiment. I explained to former Prime Minister Mr. Abe exactly what I just explained to you. And Dr. Yanagisawa, a student of Professor Ida, developed a self-healing plastic. We asked the Prime Minister to cut the plastic in half. And during my talk, it was joined back together. The presentation lasted only 5 minutes, but afterward you could see it self-heal without any adhesives. It was broken in half, but then it healed itself and became whole again. We also wanted them to experience a hard and strong polymer. And we asked Mr. Abe to press on the gels, which broke like this. Next to it, we had double network gels from Professor Gong. And we asked him to hit it with a hammer. And the sound didn't really match. He was supposed to hit it only once, but he did so multiple times. Yet it remained strong. It didn't break, which is what we aimed to demonstrate. That's an example we wanted you to see. The project was completed in 2018, and the subsequent project is the Moonshot project, which is ongoing now. This work addresses the waste of ocean plastics. With plastics in the ocean, you know they are all around. And the problem is ocean contamination with plastic. Plastic should be collected, recycled, and reused. That would be ideal, but there are plastics that cannot be collected. For example, the attrition powder from tires. It's not possible to collect it. But when they enter the water, they never degrade. We aim to develop rubbers, especially tires, that are degradable. That's the project's objective. Now, how much plastic is flowing into the water? Well, most is from inappropriate disposal. This is not really an issue with plastic itself, but rather human behavior. If people didn't litter, that would help. But there are also other problems, like discarded fishing gear. For instance, fishing lines. Remain in the water, causing issues. You may have seen this on TV or YouTube, along with tire wear powders, which are types of microplastics in water. Now, what's the problem? There are degradable polymers. However, those polymers aren't tough. Durable polymers, on the other hand, do not degrade. We need polymers that are tough during use, but degrade once disposed of. They should last a long time, but degrade quickly if they end up in the ocean. We do not have any polymers yet with both of those characteristics. But that's what we aim to develop, and that's our objective. Moreover, we want the components of the plastic to be inedible. We aim to create non-food biomass-based polymers divorced from petroleum products. If the biomass were edible, then it could conflict with the food issue. So we wanted to use seaweed and other non-edible materials. And microorganisms could also produce them. Anything edible could be used as a raw material. And we had other leading professors come together, working with different companies in Japan. We divided our roles to develop new polymers. We already have some achievements and would like to share them. This is one from Bridgestone. As I mentioned, tires don't break down easily. The polymers a tire is made of can break down. Polymers can degrade. Of course, it depends on the type of polymer, but when cross-linked, they won't degrade. However, in this project, the bottom one shows the regular cross-link, so it doesn't degrade. But this vertical line indicates biodegradability. This new rubber, cross-linked differently, will biodegrade in the ocean, and its strength is almost double. It's not too hard to make something degradable, though it's not that simple. Just having this degradable property is not enough. It also needs to be strong. Balancing these two is challenging, but using technology from a specific academia, we were able to develop this tire. I cannot share all the details, but this is what we have achieved. With higher strength, tire wear will be reduced, lowering the amount of debris produced. So it's more environmentally friendly. Another company is Kureha, which focuses on fishing lines. This black area represents the conventional fishing line. Some of you may enjoy fishing, but these lines don't degrade in the ocean. And this is very important. There are some fishing lines on the market that are degradable, but they're not strong enough, meaning they will break apart during use. So they do not really sell. But in this project, we can see that the strength has been increased. And it does degrade in the ocean. So we do have this fishing line that has garnered media attention. So if the fishing line breaks, it goes into the ocean. But after a while, it will biodegrade. For fishing lines, it seems we are nearing a solution. The bigger challenge is fishing nets. Fishing nets stay in the ocean, so they have to be strong while in use. But when they break, they should degrade. However, this is very challenging, and we're struggling to develop such nets. If you have any ideas, please approach us. This is actually a global problem, as discarded fishing nets float in the ocean, and they continue to trap fish. The trapped fish then decay inside these nets. This phenomenon is termed ghost fishing, and it's a significant global concern. It turns out the fish we consume may have been caught by these discarded nets, and we might be unaware of it. We aim to develop a fishing net that is durable during use. But when it's discarded, and especially during events like storms, when sometimes nets are cut loose to save lives, we want those nets to degrade naturally. But designing such nets is a daunting task. So let me share some technology we're trying to develop in our lab. This is PCl, which is ocean degradable. Shown by this black line, the horizontal line represents the strain, and the vertical shows stress. You can see the elongation stress isn't that high. It'll break at about 100%. But if you include 5% of this necklace structure, it becomes much stronger. Even if you increase the strain by about 5 times, it won't break. It becomes very strong. It does not just become stronger, but also more degradable, as shown by the number of days and the level of biodegradation by BOD vertically. The white circle represents cellulose, which is used as a standard material. Polycaprolactone, in fact, is a polymer that degrades less than cellulose. But if you add this necklace, its degradability is enhanced and accelerated degradation occurs. Therefore, with polyrotaxane, these necklace supermolecules can make the material both stronger and more degradable. Achieving both these characteristics is possible. And, Otani hit another home run, showing his dual capabilities. Typically, when you make a material degradable, its strength is compromised. But with this material, both can be achieved. So this could be a beneficial additive to polyrotaxane. Using the remaining time, I'd like to discuss a new project that started in April this year. This project involves a cross-ministerial strategic innovation promotion program. What's the status of plastics around us? Here's a comparison between European countries and Japan. On the graph, the green part indicates recycled plastics. Yellow represents thermally recovered plastics that are converted into heat, and the red part represents landfills. In Japan, as you can see, we are trying very hard to recycle plastics. But it's only 28%, which is lower compared to European countries. We would like to increase the percentage of recycling. That's an important issue and topic for us. In Japan, there is a high percentage of thermal recycling. You know that a lot of home waste is incinerated, as it is thrown into waste bins. But in Europe, it's been criticized because it emits a lot of CO2. So plastic should be collected and recycled. That would lead to a better result. Considering this, where there is a conventional linear economy, you produce and sell, and that's it. Most of the chemical industries generate jobs and profits From these two processes, production and sales, collection and waste oil recycling make up a similar market, which is very different. And that's because of the conventional linear economy. However, in a circular economy, everything must work in a cycle. The business model will drastically change. In Europe, many venture and startup companies are involved in the circular economy, and they are really driving the circular economy model forward. New business models emerge, new industries develop, and many new companies are established. As a result, they're advancing the circular economy. In Japan, we are lagging in this aspect. But in the future, in Japan as well, I expect to see more venture companies emerging to contribute to the circular economy. Various businesses will need to develop to match the size of the market. Personally, I'm not familiar with this area. I'm a polymer specialist. But when it comes to collecting waste and recycling, I was not knowledgeable. But now I've been involved in this type of project since last year. I've been studying hard to understand recycling better. And I believe this is the biggest reason why we haven't seen much progress in recycling. On the left, you see new plastics that have been recently made. Polypropylene, which is most frequently used. And we call this virgin PP because it's freshly made. On the other hand, there is recycled polypropylene. And the purity level is very high, even for recycled polypropylene. But if you try to create holes in a test with virgin PP, holes are made, but the plastic itself doesn't break. The entire polymer retains its shape. But with the recycled PP, once a hole is made, it breaks apart. So it's very brittle. On the other hand, at the start, the strength levels are very different between the two. So in the case of recycled products, they can't be used like the virgin product. For example, I think PP is used for electronic products, but recycled products are utilized in some areas, but not for all electronic products. The only exception where recycling is really successful is with PET bottles. Their physical properties can be recovered. In this case, several factors are involved, but we can actually make the molecules longer, so they recover as if they're like virgin PP. And we can fully recycle PET bottles. But PET plastic represents only 5% of total plastics, so most plastics fall on the right-hand side. Thus, we can mostly incinerate the rest, and even when recycled, they aren't of the same quality. Their value decreases. They get downgraded, so we can't recycle them as desired. This doesn't really contribute to the circular economy. While Japan is recycling these PET bottles, I believe this is because they are transparent. By 2025, the PET bottles in Japan will be fully recycled. We're reusing the recycled plastic. The reason it's so advanced in Japan is because in Europe, the PET bottles are a little bit colored. PET bottles in Europe, even if they are recovered, aren't fully transparent. What's great about the PET bottles in Japan is that you take off the cap and peel off the labels. And that custom is very important. Because of this, the quality of PET bottle recycling is #1 in the world. But the plastic you throw away gets mixed with other trash, becoming a kind of miscellaneous plastic, which makes it very difficult to recycle. So the best thing to do is collect pure monomaterial plastic. so that we can improve the quality and recover them to the original level. This is something we aim to achieve over the next 5 years in the SIP project. The linear economy has been ongoing, using oil and fossil fuels, but there is a regional limit. What we need to do to overcome this challenge is to develop innovative technologies. Also, changing consumer behaviors is crucial, as consumers need to prefer using recycled products. If they do not use recycled materials, we cannot effectively recover and reuse them. It's important to build a society where people are eager to use these recycled materials. Therefore, in the SIP project, we involve not just science professors, but also professors from economics and liberal arts. Both natural and social sciences are coming together. What we call integrated knowledge to promote the circular economy project. That's all from me. Thank you very much.